Swayam Prabha. Digital India. Educated India.
Let us take the first example, where whether I solve in an inertial frame or non-inertial frame, it does not matter. If I take a car and I have a pendulum in it, and the car is accelerating to this side with an acceleration a, what would be the position of the pendulum in this car? You can almost feel that the pendulum is going to be like this if the car is accelerating. But why should it be? With this angle here, theta. We will solve this problem both in the non-inertial and the inertial frame. In the inertial frame, that is frame from outside, the free body diagram of the pendulum in this position is that on the bob there is a tension T, force mg pulling it down, and as a result of these two forces the bob is accelerating to the right with an acceleration a, because the car is accelerating and the bob is stationary in the car. If this angle is theta, then you can see that T cosine of theta is equal to mg, because the ball is not moving up and down, and T sine of theta is equal to ma, because the bob is accelerating towards the right with an acceleration a, and that gives you tangent of theta equals a over g. What if I look at the same problem in a non-inertial frame? And what frame do I choose? I choose the frame which is attached with the car and moving to the right with it. In this frame, you see the bob in equilibrium under the force mg, tension T, and a fictitious force ma to the left. Notice that when I am sitting in the car, the bob or the pendulum is in equilibrium position, because with respect to the car frame it is not moving at all. The three forces are to be balanced for equilibrium, and that gives you T cosine of theta equals mg and T sine of theta equals ma. Notice the difference. In the inertial frame, T sine theta gives you an acceleration towards the right. In the non-inertial frame, T sine theta balances the fictitious force, with the final result of course being the same, that tangent theta is a over g. So you see two ways of looking at the same problem, and of course I should get the same final answer, same effect. As I commented earlier, that I can think of this the force, fictitious force in a uniformly accelerating frame as a gravitational force is illustrated beautifully by this example, because now the pendulum is at an angle theta from the vertical, and that tangent theta is given by a by g. If I look at it from the gravitational field point of view, the pendulum is actually in a gravitational field which is the sum of these two gravitational fields, acceleration g this way and acceleration a this way. So the net gravitational field is the sum of these two, and that is in this direction, which is shown here by the big arrow. And this is at an angle theta with tangent theta equals a over g. Any pendulum in its equilibrium aligns with the gravitational field. So no wonder that the pendulum is aligned with this in its equilibrium position. And that is the explanation for this. So you can see that thinking of this field in the pseudo force or pseudo field in a non-inertial frame is like a gravitational field is meaningful and gives you the right answer. Using this, now we will solve a slightly more complicated problem, which will show you that actually going to non-inertial frame sometimes makes life very, very easy. The problem that we solve now is, suppose there is a pendulum and its support is suddenly accelerated to the right with an acceleration a. Which way would the pendulum move and by how much angle? That is the question that we want to answer. First, let us solve this problem in the inertial frame attached to the ground. I am solving it for two reasons. One, you will see how to solve a difficult problem, and two, when you compare the solution in an inertial frame compared to the solution in a non-inertial frame, you will see the effectiveness of solving problems in a non-inertial frame sometimes. So, in this case, when this accelerates to the right, let us assume that the pendulum also swings to the right with this angle being theta. I am choosing it to swing to the right so that this way is theta positive and theta dot will be greater than 0 for pendulum to the swinging to the right. This I do because now I am going to fix my frame like this, x and y, and initially let the pendulum, I will plot it with blue, be here with the bob at the origin. And as the pendulum its base is its pivot point is accelerated to the right with a, we are assuming that after some time t, the pendulum would look like this, with it having rotated by an angle theta to the right with respect to vertical. As I commented earlier, I choose this direction as theta positive because then theta dot and x dot have the same positive direction, and that is important. Otherwise, I may have to change sign along the way. Let me write for the bob position its coordinate as x b and y b, and for the support let me write x and y. So, let me make this picture once more. What we have is this frame at t equal to 0. This is the way the pendulum is, and after time t, the base has moved here, the pendulum has moved this way by an angle theta. This distance is 1/2 at square because the base or the support of the pendulum is moving with an acceleration a. This is xb, yb, and y of the support does not change. Let the tension in the string be T. Let us write the equations of motion for the ball. I am going to have x b double dot is equal to minus T sin theta divided by m. That is my equation 1. I am going to have yb double dot is equal to T cosine of theta over m minus g. That is my equation 2, because on the bob in the vertical directions there is t cosine theta component and a g component. How many unknowns do I have? I have unknown xb, I have unknown yb, I have unknown theta, and I have tension T, 4 unknowns. So, I need 2 more equations. Those equations are provided by the relationship between xb, yb and the coordinate of the support. The support has moved by a distance 1/2 AT square, and that is equal to xb minus, if the length of the pendulum is L, it's going to be minus L sine of theta. Similarly, I am going to have y of the support equal to yb. This is yb plus L cosine of theta. This is my equation 3 and equation 4. I have gotten 4 equations, 4 unknowns, and I can solve for them. So let us do that. Let me rewrite the equations once more, and then we will solve for the problem. So I have x b double dot equals minus t sine theta divided by m. I have y b double dot equals t cosine theta divided by m minus g. I have 1/2 AT square equals xb minus L sine of theta. If I differentiate this once, it gives me AT equals xb dot minus L cosine of theta, theta dot. If I differentiate it once more, it gives me A equals xb double dot minus plus L sine theta, theta dot square minus L cosine of theta, theta double dot. And let me call this equation number 3. Similarly, y equals yb plus L cosine of theta gives me y dot is 0, 0 equals yb dot minus L sine theta, theta dot. Differentiating it once more, I get 0 equals yb double dot minus L cosine theta, theta dot square minus L sine theta, theta double dot. Let me call this equation number 4. So I have equation number 1 here. We box them. This is equation number 1, equation number 2, equation number 3, and equation number 4. Let me substitute for xb double dot in terms of t and yb double dot in terms of t in equation number 3 and 4. And what do I get? I am going to get xb double dot, which is minus t sine theta over m plus L sine theta, theta dot square minus L cosine of theta, theta double dot is equal to A. And for the y equation, so I am going to get yb double dot, which is t cosine theta over m minus g minus L cosine of theta, theta dot square minus L sine of theta, theta double dot is equal to 0. Let me call this equation number 5 and equation number 6. Multiply equation number 5 by cosine of theta and multiply equation number 6 by sine of theta and add. If I do that, I get the first term t minus t sine theta cosine theta plus t cosine theta sine theta, that cancels. Second term L sine theta, theta dot square cosine theta minus L cosine theta sine theta, theta dot square, that cancels. So I get minus g sine of theta. These two terms give me minus L cosine square theta plus sine square theta, that is 1, theta double dot is equal to A cosine of theta. In other words, L theta double dot is equal to minus A cosine of theta minus G sine of theta. That is my equation for theta. I have done my job. I solved this equation and I can get all the answers. Let us do that. So, the equation that we have gotten is L theta double dot is equal to minus A cosine of theta minus G sine of theta. Let us put theta double dot equals 1/2 d by d theta of theta dot square and integrate it to get L by 2 theta dot square is equal to minus A sine theta plus G cosine theta plus a constant C. However, at theta equal to 0 when it started, theta dot is equal to 0, and that gives me C equals minus G, and therefore, L by 2 theta dot square comes out to be minus A sine theta minus G 1 minus cosine of theta. That is your solution for theta dot square. So, what we have got is, when I have a pendulum at a support and suddenly the support moves with an acceleration A, I am going to have the angle of this change by L theta dot square is going to be equal to minus A sine theta minus G 1 minus cosine of theta. Note 1, theta cannot be positive. If theta becomes positive, the right hand side would be negative, and that will give you theta dot square to be negative, which cannot happen. Therefore, the pendulum has to swing in negative theta direction. It has to swing back. So, after some time, its position would be something like this. It would have swung in theta negative direction. And where does it stop? So, question we ask, where is theta dot square 0? One answer of course is theta equals 0, which point we started with, and the second point is going to be 0 equals minus A sine theta minus G 1 minus cosine theta, which I can write as minus 2A sine theta by 2 cosine theta by 2 minus 2G sine square theta by 2, and that gives you, okay, let us see, this sine theta by 2, one of them drops out, this 2 drops out, and that gives you tangent of theta by 2 equals minus A over G. So, theta dot square becomes 0 again when tangent of theta by 2 is minus A over G. So, here was the support which suddenly moved towards this with acceleration A, and the final position is such that at a point such that this angle is alpha, then tangent alpha by 2 is minus A upon G, or alpha just in magnitude is equal to tan inverse A over G times 2. This has a beautiful interpretation. Remember earlier, this was the angle which has tangent theta equals A over G, that angle where the new equilibrium point of the pendulum was. So, in a way, the pendulum has swung across the equilibrium point by as much angle as it was away from it on one side, and this is a solution that we have gotten by solving an inertial frame. Let us see now how would the solution look in a non-inertial frame. Non-inertial frame moving with the support. So, I look at this whole thing in a non-inertial frame moving with the support. In that frame, this is the equilibrium position of the pendulum, such that this angle is tan inverse A over G. So, in this non-inertial frame, this is the equilibrium position. So I am looking at the pendulum as if it is moved to one side from the equilibrium position by an angle tan inverse A over G. Recall what happens if I have a pendulum from the equilibrium position. If it is raised by an angle theta to one side, what happens when it swings back? It swings exactly by the same angle to the other side. So in this frame, accelerating frame, the pendulum will swing across the equilibrium point exactly by the same angle as it was initially to the one side, and that is going to be tan inverse A over G. So the total swing of the pendulum from the vertical is equal to 2 tan inverse A over G. Now I would like you to appreciate the power of having solved this problem in a non-inertial frame. While solving in the inertial frame, I had to do work with many equations, 4 or 5 equations, and had to manipulate a lot of them. On the other hand, when I went to non-inertial frame, the problem could be solved in 3 or 4 lines, and that is the power of using non-inertial frames in certain problems.